morning, we will continue our discussion which was yesterday related to different types of constitutive equations that we talked about. So the constitutive equations means that we are, can somebody tell what do constitutive equations? They have the relation between stress and strain, and their property of what? The equations will be same for all objects, or they will be different. Okay, so these equations, or rather the coefficients of these equations, they will be different for different types of material, or the number of unique coefficients that are required to define an isotropic material would be different than the number of unique constants that you require for an orthotropic material, and that is something that we have seen. Anybody remembers how many unique constants are required for isotropic material? So that is for, in general, anisotropic material, you are right, 21 constants are required to define a general material. Isotropic material, that is having properties same in all directions. So how many? You require only 2 constants for isotropic material. And for orthotropic material are the materials like a rolled plate. 9 constants are required for orthotropic material. And the constituent equations take the form like, so yesterday you have written in terms of epsilon and sigma, but you can also write this equation in terms of sigma and epsilon. So the equations can be written either sigma in terms of epsilon or epsilon in terms of sigma, the way we wrote yesterday's class. Now we have seen how many unique constants are required. Now for homogeneous material, these constants will remain same anywhere in the body. So if this table is a homogeneous material, whether you consider, and if this is the origin of your coordinate system, so at this point, whatever are the constants, whatever 21 constants are required to define the stress-strain relation at this point, they will remain same at every point of this particular equation. But if this particular material is non-homogeneous, then these constants will change as you change the location. So these particular constants for non-homogeneous material, so AIJR between stress to strain, BIJR between strain to stress, what we yesterday wrote. So they are function of the XYZ coordinate. So that means depending on which location you are looking for, you will have different values of these constants. Okay, and for linear materials, all these constants are constants. That means they do not depend either on the values of stress or strain. But for non-linear materials, So what it means is that if the material is non-linear, then these constants will start depending on the values of epsilon x and sigma x at that particular point. What it means, for a simple case, we can illustrate that one of these constants is modulus of elasticity. So if you have linear material, the modulus of elasticity is independent of epsilon or sigma. So till the time the material is linear, whatever may be the value of epsilon and whatever may be the value of sigma, the E value, that is slope of this line, is independent of epsilon or sigma. Wherever you take the value of E value, that remains the same. So that is what is meant by linear relation between stress and strain, or the constitutive equations are linear. When you are going in plastic zone, you will find that at this point, if you take slope of this particular stress to strain curve, which corresponds to the E value or one of the constant in this constitutive equation, so this E value will be different than the E value at another point. So at every point, the E value, which is one of these constitutive equations coefficients, those will start depending on the value of what is the instantaneous value of stress and strain at that point. Depending on that, these constants will keep on varying. So that makes the problem more complicated. So this equation will be non-linear because these constants themselves involve the value of epsilon x, which you are trying to find out, epsilon x or sigma x or both of them. So it becomes more complicated relation. The real materials, when we are dealing with the plastic zone, this particular constitutive equation will necessarily become non-linear, and that becomes very complex case to be handled. So for the purpose of this course, we will be looking only at the linear material, so we don't have to worry about these complexities, but you should be aware of how these constitutive equations or the coefficients of the constitutive equations will be different for non-linear materials and how they will be different for non-homogeneous materials. So non-homogeneous materials, they could be isotropic, that means you can have non-homogeneous material which will have properties which are equal in all directions. That will require only modulus of elasticity and Poisson's ratio to define them fully. But E value and Poisson's value at one point will be different than E value and nu value at the other point. So that is the difference between non-homogeneous material. However, the material is isotropic. That properties at every point, they are equal in all directions, but they are different at different locations. So that is the difference that you should know. So what is homogeneous, what is isotropic, and what is non-linear, so you should be very clear among yourself. So now we will look into some expressions which are commonly used in solid mechanics. So those are known as Lamage coefficients. So for isotropic material, instead of talking about E and nu or E and G, we talk in terms of what is called as a Lamage coefficient, and we'll just understand just introductory knowledge about what are these Lamage coefficients and how they can be used for calculation. Because some of the books, some of the higher solid mechanics books, you may encounter rather than the material properties, you will have the material properties are defined in terms of Lamage coefficients. So that is what we will look into. So again, these coefficients are defined for isotropic material, the properties which are identical in all directions. So consider a situation where you have a particle which is having principal stresses and principal strength and you choose a coordinate system such that your axes are aligned in the principal direction. So, in that way, you will have one plane on which sigma 1 and epsilon 1 is acting. Okay, there is one more property of isotropic material. It is that proof we have not covered, is that the direction of principal stresses and direction of principal strains, they are identical for isotropic material. So, whatever is the principal stress axis, maximum principal stress axis, the same axis will be there for maximum principal strain as well. So it can be proved, but that proof you can get in the textbook, but we are not covering here. So if sigma 1 is the direction of first principal stress, epsilon 1 will also lie along the same direction, and we have chosen the coordinate axis such that they are aligned along the principal directions. So in the second plane we will have sigma 2 and epsilon 2, and the third plane we have sigma 3 and epsilon 3. And since these are principal directions, the planes on which they are acting are the principal planes. So what will be the value of shear stresses of these planes? What will be the value of shear stresses on these planes? So by definition, the principal stress, the shear stress has to be 0. So there is no shear stress which is acting on this particular set of planes. So we'll write in this particular case the sigma 1 can be written in terms of constitutive equations in terms of epsilon 1, epsilon 2 and epsilon 3. So we'll write it as A times epsilon 1 plus B times epsilon 2 plus C times epsilon 3. Where ABC are the coefficients of the constitutive equations. Now this is one point which you have to understand. Now B relates sigma 2 and epsilon 2, and C relates epsilon 3 and sigma 3. So that is the relation. The B and C relates between sigma 1 and sigma 1 and epsilon 2, and C relates to sigma 1 and epsilon 3. Now remember that the material is isotropic, that means all properties in any direction would be same. So what this point coefficient A represents is that if you apply a strain in direction 1, that is if you pull in the direction 1, the stress generated will be given by this particular sigma 1. So this particular A will be corresponding to material property which is modulus of elasticity. And what would be this B and C would correspond to? So yesterday we had seen a similar expression, or we dealt with that. So sigma 1 is given as, or rather we wrote the equation in terms of the strains in one direction in terms of stresses in the other direction. So similarly the stresses also can be represented in terms of strain. So this E will be some function of E, modulus of elasticity, and B and C are related to something like Poisson effect. So when you apply a strain in a particular direction, the stress gets generated in the other direction. So just like if you apply stress in one direction, there is a strain which gets generated in the transverse direction. Similarly, if you apply strain in the transverse direction, there will be stress which will be generated in the other perpendicular direction. So that is what these B and C are relating to. Now since the material is isotropic, so if epsilon 2 generates some value of sigma 1, which is related by this proportionality constant is B. That means if you apply 1 unit of sigma 2, you get B units of sigma 1. And in the second case, this epsilon 3 is nothing but a strain in third direction. So if you apply unit strain in third direction, you will get C units of sigma 1. So what we can talk about relation between B and C. So will there be any relation between B and C if the material is isotropic? I'll repeat once again. If you apply unit strain in second direction, you will get B units of stress in the first direction. If you apply unit strain in third direction, you will get C units of stress in one direction. So what should be the relation between B and C? Okay, why? Can you elaborate why they should be equal? That's right. So considering this case, we are concentrating on this particular direction. So whenever a unit strain is happening in sigma 2 direction, we are getting some component of this sigma 1 is consisting of the effect of epsilon 2, and there is some effect because of epsilon 3, which is also coming here. So if you apply unit strain here, some components get generated here. If you apply unit strain here, another component gets generated here. And since both of these are transverse direction and material is isotropic, whatever happens in direction 2, exactly same thing should happen in direction 3 as well. So if you apply unit strain either in vertical direction or in this horizontal direction, the same amount of stress should get reflected in the first direction. So that is why this B and C, they are nothing but identical. So although we are having their three unknowns, because of isotropy, we are having B equal to C. So we'll rewrite this equation in a particular format. So what I have done here is I have added and subtracted B times epsilon 1 in this particular equation. So in the last term, it becomes B times epsilon 1 plus epsilon 2 plus epsilon 3, and same B into epsilon 1 I have subtracted, so I get A minus B times epsilon 1 in this particular case. Why we are trying to do this? That is summation of strains in three direction, it has got some relation. Have you come across this in strength of materials? What is epsilon x plus epsilon y plus epsilon z? It is related to some other kind of strain. It is related to bulk modulus, but this particular, so it is a volumetric strain, that's right. So this particular thing is the volumetric strain. Now volumetric strain has got some importance in some aspects of solid mechanics, where we are trying to develop some failure theories. So one of the failure theory is what is commonly used is von Mises theory of failure, which is also known as distortion theory, distortion energy theory. So in that particular theory, it is assumed that whatever failure occurs, it occurs only because of the distortion of the material, and whatever volumetric expansion or contraction is happening, it doesn't lead to the failure. So this particular quantity, which is the volumetric strain, is something useful in that kind of analysis and in some other calculations of solid mechanics as well. So that is why this particular expression we have brought in into this particular equation. So this particular quantity, we can write this particular equation in following manner. So we can write sigma 1 as lambda times volumetric strain so this A minus B I am calling as 2 times mu, and this B value I am calling as lambda. Let me not write here, otherwise it is not division of this term. So this is 2 times mu and this is lambda. So we can write this equation as sigma 1 equal to lambda times the volumetric strain plus so this delta is volumetric strain, which is also termed as the cubic dilatation. So that value can be used in this particular calculation. So what we have done is nothing new. It is just, rather than writing in terms of modulus of elasticity and Poisson's ratio and modulus of rigidity, which is the common way of representing the relation between stress and strain, here we have introduced the 2 new parameters which are known as the Lamè's coefficient. So it is just renaming the terms which we are familiar with, but those who are working in the higher solid mechanics, these coefficients are more handy and they provide more better way of representing certain material behavior. So that is why what is the importance of these parameters, and lambda and mu, they are called as Lamè's coefficient. Similar to this equation, you can write exactly in the same manner the equation for sigma 2. So what will be the value of sigma 2? What should be the value of sigma 2? Taking clue from the first equation. So the first term is consisting of all the 3 strain values, so that will remain unchanged. So it will be lambda times delta plus 2 mu times, it will be epsilon 2, and sigma 3 will be lambda times delta plus 2 mu epsilon 3. So stress and strain can be written in terms of the Lamè's coefficient, and as expected for isotropic material there are only 2 coefficients are required, and that are this lambda and mu. So instead of talking about E and nu or E and modulus of rigidity, there is one more terms that we are introduced. So the use of this is more for the theoretical analysis rather than for regular engineering calculation. We don't use this Lamè's coefficient. We go ahead with our regular modulus of elasticity and other terms related to that. But this is again for your information that such thing exists. You should be aware that what is Lamè's coefficient you should be aware of, and they are nothing different than just another expression to the material behavior which is given in terms of the modulus of elasticity or the Poisson's ratio or the modulus of rigidity. So that is the new thing. In fact, all those numbers can be represented in terms of these lambda and mu values, and just for the reference I am reproducing them here. So you need not remember this expression, but just to show that how these numbers will be used. So the three known material properties, modulus of elasticity, the Poisson's ratio, and the modulus of rigidity. In fact, the modulus of rigidity is identical to the constant mu, that is Lamè's constant mu is nothing but the modulus of rigidity. So that is the topic that concludes the constitutive equations. One question. Okay, any questions on this particular topic? So next, move to the next topic, that is, till now we have been dealing only with the coordinate system, which is Cartesian coordinate system. Now there are some objects which can be better analyzed using another coordinate system. So how many coordinate systems you are aware of? I believe in the coordinate geometry or in the geometry you must have come across other than coordinate. Yeah, what are those three? Spherical, polar and normal. That is the Cartesian coordinate system. So Cartesian coordinate system in terms of XYZ axis, and that is the one which is more commonly we are using. The second coordinate system is the cylindrical coordinate system, which is also known as polar coordinate system, and the third is spherical coordinate system. Now whatever equilibrium equations we developed in the previous classes, they were with the Cartesian coordinate system. The similar equations we can develop in the polar coordinate system as well as in the spherical coordinate system. So the use of polar coordinate system or cylindrical coordinate system has some importance, so that is why we are discussing, obviously that is why we are discussing it here. So let's understand situations where this cylindrical coordinate system would be useful. So let's identify some situations where use of this coordinate system would be advantageous. In the polar or cylindrical coordinate system, the coordinates will be represented in terms of what is its radial location. So first we have to define some axis of rotation or axis of symmetry about which we are defining the coordinate system. So that is conventionally called as a z-axis. R coordinate represents from the z-axis what is the distance, radial distance to the point that we are talking about. So that is R. And theta, we have to define some theta plane or the reference plane. So this is the plane that we are talking about. So with respect to this plane, if your point, how much angle it is making at that represents the theta coordinate of this particular plane. And z is the elevation of this particular point from the origin of your coordinate system. So with respect to the origin, how much up or down this point is represented by this z coordinate system. Now this particular coordinate system is beneficial in terms of components which are having circular symmetry. So essentially any objects that you can obtain by revolving a cross section about an axis of symmetry, so those components would be ideal to be analyzed using this cylindrical coordinate system. So just tell me some components which are circular symmetric, or the geometries or those objects can be developed by revolving some cross section about the axis of rotation. So can you tell some components? Okay, give me some practical components rather than geometric names. Ball bearing. Which part of the ball bearing? In the sense, the ball bearing, you have the inner casing, outer casing, and then you have the balls. The ball bearing is the assembly. So out of this assembly, which component is cylindrically symmetric? This entire ball bearing, is it circular symmetric? What do you mean by circular symmetric is that you take a cross section and then you revolve about certain axis and then you get, so in this case if you revolve this rectangle you will get a cylinder. So can you generate this ball bearing, the assembly of ball bearing by this process? We cannot obtain because there is gap between the balls which cannot be obtained. So the assembly is not the one which can be analyzed using the system. But there are some parts of this ball bearing which are ideal, which are suitable for this cylindrical coordinate system. So which are those components? The inner race and the outer race, or the inner cylinder and the outer cylinder. So those are ideal for the polar coordinate system representation. What about the balls? Individually the balls can be represented. So should they be represented in cylindrical coordinate system or spherical coordinate system? So it is ideal that they can be represented in terms of the spherical coordinate system. That's right. So can you represent a sphere in cylindrical coordinate system? So what I mean by cylindrical coordinate system is you define some cross section. If you revolve that cross section, you should get the geometry. So can you get the geometry of a sphere by revolving some cross section? A semicircle. So you can take a semicircle and generate. So the spherical geometry can be represented both in cylindrical coordinate system as well as the spherical coordinate system. Defining it in spherical allows us some advantages in terms of the expressions that we get. But yes, so the first part we discussed here. So there is inner or outer race of cylindrical bearing. Any other component which you have come across? Which you have observed so many. Okay. So shafts which are used for power transmission. So those are cylindrical components. So gears will have similar situation as the ball bearing. So gears will have two. If you are talking about the ring of the gear, it is circular symmetry, but this particular symmetry, so they are known as sector symmetry geometries. So they are not ideal for analysis using cylindrical coordinate system. They can be, but it is not. That is not what we are discussing here. Okay, assuming that nuts are having cylindrical shape. So cylindrical nut and bolt, and you have to ignore the threads because thread has got a spiral shape. Okay, so there will be many more components. So can you think of something more? Roller. Roller. That's right. So which roller you are talking about? Okay, road roller. That's right. Any other component that you have come across? Roller in the conveyor belt. Okay, so these components gives you idea that components that we are talking about. There is one more component which is subjected to a type of loading. So there are, in addition to this, there can be pressure cylinders. Which are also circular symmetric. Now each of these components, they are subjected to different types of loadings, and we need to consider those loadings in order to analyze them further. There are certain components whose geometry is symmetric, circular symmetric, as we are already listed here. But there is one more condition, that the loading on those components, that also should be circular symmetric. So I'll repeat once more that out of these components, let's try to identify some components which are having circular symmetry, which all of them are having, but the load which acts on them, that also should be circular symmetric. That is the load, if you consider along the theta axis. So this is your component which is circular symmetry. So this is the theta direction. So the load at any theta should be identical. So load should not vary in the theta direction. So that is additional condition. So if the theta load is constant in theta direction, these components are called as axisymmetric components. So our discussion in this particular course will be with respect to these axisymmetric components. We will be discussing the theory of axisymmetric components. So for component to be treated as axisymmetric, its geometry should be created from evolution of some cross section, and the loading on that component, that also should be circular symmetry, or it should not vary in the theta direction. So let's take one by one each of these components. So if you consider a cylindrical bearing, what kind of load acts on that bearing? So let's take, okay, here we don't have cylindrical bearing. What bearing we are having here is a thrust bearing. So that is different than what we are talking here. Okay, so let's consider there is a shaft, and here you are having the bearing in which the shaft is rotating. So the load on that bearing, is it, so theta direction is along the circumference of the bearing. So does the theta remain same, the load remains same in the theta direction for that bearing? So you have the bearing, and we are talking about the only inner race which is circular symmetry, and there is a shaft on which some reaction is going to act. So there is some weight of the shaft which is acting on the bearing. So that is the loading condition which is happening. So is this loading condition symmetric in theta direction? It is not. The theta, if you plot this load, it is highest at this point, and at remaining points it keeps on diminishing. If you consider point load, it is zero everywhere else except at the bottom point. If you consider pressure loading, the pressure will be highest at the center, but it will keep on reducing as you move in the theta direction. So this is not the case of the axisymmetric problem. I mean, this problem can be solved using the general cylindrical coordinate as a general cylindrical coordinate system problem, but that is much more complicated. However, in this course, since we are focusing on axisymmetric problem, let's understand what is an axisymmetric problem. So can this bearing problem is there any load on this bearing which you can treat as axisymmetric? So this load, because of the external weight of the shaft, that cannot be considered as the axisymmetric loading. Can you just close the door? Okay, so this particular inner race of the bearing, so can you think of any other load which will be axisymmetric or which is not varying in the theta direction? Okay. So what you are talking, like the bearing in the fan, so you, of course there the construction is different. So you are having this particular shaft and then you have the thrust bearing where you have balls here. So this particular string, if you consider, it will have load which is acting at this particular location where the spheres are sitting in the onto the ring. So this particular loading is, if you ignore that these balls are at discrete points, if you consider the gap between balls is very small, in that case whatever force is acting at this particular point, if you uniformly distribute it all over the circumference, I think that is what you meant. Okay, I will let you mean in that particular direction. So this is not exactly axisymmetric problem, but for the purpose of simplification, we can simplify this problem as axisymmetric by making this load to get uniformly distributed over the entire circumference where the balls are fitting onto that particular bearing. Okay, so that would be one example of axisymmetric problem where the bearing would be facing. But let's consider it is not thrust bearing. We are talking about regular bearing and a cylinder which is rotating. So can you think of anything which a rotating cylinder, what kind of theta symmetric loading you can get? Imagine like inner race of the cylinder, you have a cylinder which is spinning about an axis. So what loading comes to your mind? Okay, the clue is that it is not external loading, but it is intrinsic loading. The centrifugal force, or because the cylinder is rotating, and if it is rotating sufficiently high, all the particles will try to move away. So that is a kind of body force that will be acting on this particular cylinder, so that all particles trying to fly out. So that is also an example of axisymmetric loading. So you have a cylinder which is spinning in a direction. So all particles will try to fly out. And this loading at any theta you consider, it will be identical. It will be uniformly distributed all over this geometry as long as the mass distribution is uniform. So with the geometry being axisymmetric, geometry being symmetric, circular symmetry, that mass distribution also will be symmetric, and hence the force which arises from centrifugal force, that also will be symmetric. So that is also a kind of axisymmetric loading, and in this course we will be analyzing how to calculate the stresses because of this type of loading. Okay, so let's quickly go through shafts. What is the type of loading? So shafts also will have the centrifugal force, so that is an axisymmetric loading. So other than the axisymmetric, other than the self weight, what other loads come on the shaft? One is wherever they are supported, there will be support reactions. So will support reactions be axisymmetric? So it is like this bearing problem only. So just like bearing reaction, the equal and opposite will come on the shaft, so that loading will not be axisymmetric. So any other loading on shaft you can think of which is axisymmetric?
metal that I will need to select the layer tires of metal that I will need to the rollers.
Okay.
But there will be the axles.
Okay, mechanical loading you will find it difficult. Other than body force, mechanical loading will not be there. So it is difficult to imagine unless somebody has thought. It is one of the important loading or rather dangerous loading which appears in mechanical design, and that is the thermal loading. So often one ignores that thermal loading, but if this shaft, many of the shafts in order to reduce the weight, they are made hollow. So you will be learning that later on. But if there is a hollow shaft and inside there is some heat generation is there, then this particular skin will be at high temperature and the remaining part will be cold. So this will try to expand and that will create the thermal stresses, which will be again circular symmetry. So at any, if this temperature distribution is circular symmetry, then these thermal stresses also will be circular symmetry. So that would be an example of the axisymmetric thermal loading. In this course we will not be dealing with that, we will just have introduction to how to do this analysis, what is known as thermoelastic analysis. So we will just have hint towards how to solve this, but we will not be solving this problem. We will be solving this centrifugal force problem. Okay, cylindrical nut and bolt, okay, they will be having similar road roller and others, they will have similar loading. They will have some kind of reaction loading coming on them, so which is not axisymmetric. But its pressure cylinders, you can think of some axisymmetric loading. The internal pressure or the external pressure which acts on the cylinder, it is independent of the theta. So any point, because of the property of the fluid, the pressure will be same any point in the internal volume of the cylinder. So that is why this would be axisymmetric loading. So we will consider this two designs. One is this pressure cylinder and second is this rotating discs or rotating masses, how to calculate stresses in them. So these two problems will be analyzing in this particular course. So we will know how to calculate the dimensions for the bodies which are undergoing this kind of loading and geometry. The way we will be developing these equations is starting with the equilibrium equation. So we have developed the 2D in 3 dimension. We have done in Cartesian coordinate. We have developed the equations of equilibrium. So we have the 3 equilibrium equations which we derived by considering the equilibrium of the forces which are acting on these bodies. So anybody can tell what is this gamma x? That is the body force in the x direction. So in the Cartesian coordinate system, you can only take care of bodies which are having linear acceleration, whereas in the polar coordinate system, this particular thing would be a radial thing which is useful for the spinning bodies. For the spinning bodies, the force is always in the radial direction. So if you want to use this particular equation and try to model the spinning shaft, it would be very difficult because this gamma x will be different at different x locations. In the sense its value will be, x component of the centrifugal force will be different at different points. So in the similar fashion, we have the equilibrium equations for the cylindrical coordinate system, and that we will be deriving in the next week's tutorial. So derivation we will not covering in the class, but we will derive these equations in the tutorial. So here I will just present those equations and that will be our starting point for solving the problems that we discuss, the 2 problems, that is cylinder subjected to internal or external pressure and the rotating discs, how to calculate stresses in such components will be calculating using the equations what we talk equations which we'll be discussing now. So the equations in the cylindrical coordinate system are as follows. So here, and we will be deriving one of these equations in the next week tutorial. So you know how these equations are developed. The procedure is similar to how we develop the equation in the Cartesian coordinate system. So the three equations are with the similar form that we have seen for the Cartesian system. So first equation we are having the three stress components and the body force. So here also we are having the three stress components. So first is the linear stress component or the axial stress component, and there are two shear stress components, and the third one is the term which is something was not there in the earlier case. So we'll see why this term appears, and the last term is the body force. So body force in radial direction, body force in axial direction, and body force in the circumferential direction. So theta direction is the circumferential direction. So what it essentially means, the way the stresses are represented here, the convention is same as that we followed in the cylindrical, the Cartesian coordinate system. So the element which is shown here, I think the last benches may not have difficult. I don't think I can expand it further. It is the highest I can go. So in this case, the faces are defined in the same manner. So in cylindrical, we have the x face, y face, z face corresponding to the orientation of normal to that particular face. So in this case, if we take this particular face, so this particular face has got normal which is in the radial direction. So this is the R plane. So as a result of which the stresses which are there, so the normal stress on this plane is equal to sigma R. The stress which is in this direction, so this is acting on R plane and it is acting in the circumferential or theta direction. So this is tau or theta. And the other shear stress is the stress on the R plane acting in the Z direction. So this is tau R Z. Now let me just zoom in so that others can also see. So there is one component which is shown here. So can you name this particular component? What will be the designation for this component? So it is tau because it is a tangential stress. So on which plane it is acting? The plane is given in terms of the normal to that plane. So you have to first see what is normal to this plane. So this is the Z axis. Okay, I did not discuss the axis. So this is, so radial is anywhere in the radial direction is radial. Theta is in this direction and this is the Z direction. So maybe I did not define this earlier, so you have the confusion. So if this is the Z direction, so normal to this plane is Z direction. So what would be this stress component termed as? ZR or RZ. So the symmetry of cross shears applies to this system as well. So this is ZR, and similarly the other components can be termed out. So let's talk about this component which is not designated. So the component which is drawn here, so how will you designate this component just to verify? So this particular plane, the normal to the plane, so this is more visible in the top view. So in the top view you will have this particular center as given here. So this is the center. So the normal to the plane is in the circumferential direction. So this is the theta plane, and the force which is acting is in which direction? So this is in the r direction. So this becomes cos theta r or r theta. So that is the way the stresses will be designated in the polar coordinate system. So nothing new, it is same as what we did in the earlier case, and that is what we will consider. Okay, so using this particular set of equations, we can develop our solution to our problems. Before we close, we will just understand how these equations will become simpler in the case of axisymmetric problems. So these particular equations are for general cylindrical coordinate system. For axisymmetric problems, these equations take more simpler form. So we'll understand how these equations look in for axisymmetric problems, since we are short of time, so I will just quickly do it here, and then next lecture we will have more elaborate discussion. In the axisymmetric problem, what happens is that since the loading is axisymmetric as well as the geometry is axisymmetric, we will have the components which corresponds to the circumferential direction, that is tau r theta or tau theta z. So these two components will become 0. The reason for this is that in order for this particular tau r theta to occur, you will require a loading which will cause distortion in the theta plane. So for axisymmetric problems, the distortion cannot happen in the theta plane, and that is why these two components are 0. Means I am just jumping to the conclusion without elaborating. So I just want you to think about this before you come to the next class, where we will discuss it in more details. So for axisymmetric problem, these two conditions hold true. As a result of which, you will have this particular term vanishes from the first equation. This term vanishes from the third equation. Again tau theta z, they vanish. Tau theta is again 0, so this term gets vanished. Gamma theta is the body force in the circumferential direction. So what it means is that at every point you will have some body force in the theta direction. So all these forces are in theta direction. Then you think of a situation where this can happen. A body force which is in the tangential direction. Every point, when this body is accelerating when it is circularly accelerating, so at that point this particular thing will happen. So this condition will lead to change in the theta position of each of the particles. So one of the condition of the axisymmetric problem is that there should not be any distortion or any displacement in the theta direction. So all particles remain where they are in the theta direction. So as a result of which this particular loading cannot be considered as axisymmetric loading. So as a result of which this particular gamma theta also becomes 0, and this term, that is sigma theta, rate of change of sigma theta in the theta direction, so that also we'll see in the next class, that it also must be equal to 0. So the fourth equation, third equation automatically gets satisfied, and the remaining two, so for axisymmetric problem we have to deal with only these two equations, and using these two equations we will solve the problems that we are handling in the next one. Okay, so we'll stop here for today, and we'll take this axisymmetric problem in more detail for the next class.